As you're working with solids of revolution, I thought I would offer up a couple of different technologies that might be useful in visualizing some of these. So I'm going to start with the regular Desmos graphing calculator. And this is something that can be used just to visualize regions in the plane. By the way, I am going to be looking at this particular example from our textbook. So this is the region between y equals square root of x and y equals 1 over x, from x going from 1 to 4, being revolved around the y-axis. So sometimes it can be helpful just to start with looking at the region in the plane. And for that, I think that Desmos is one of the easiest tools to use. So I just put in those functions. When you're putting in functions, there is a calculator here, and functions are in this button, but also a lot of them actually have keyboard shortcuts. So I'm going to put this away. I hardly ever use that keyboard. So if I want to say sine of x, then I just type in sine. And if I want to say the square root, I type in sqrt. And the minute I hit the t, it just turns into a square root. So these are the things that I would do just to be able to visualize that region. Now, if I want to visualize that region on the xy plane in a three-dimensional space, I might go to Desmos 3D. And so this shows, basically, it should be exactly the same picture as this other one. You can kind of see it here in a little thumbnail. But the xy plane is laid down flat here, and then there's a new axis poking up. And you can take this and you can drag it around. And there's a couple of buttons that I can say, this is the default orientation, and this one's kind of a nice orientation, which shows you the xy plane. And so this is almost identical to the view from the Desmos, regular Desmos calculator. I have put in exactly the same things in here. I want to note that these equations mean something different. If I write y equals the square root of x in a three-dimensional plane, technically, that actually is a sheet. Okay, that allows a lot of z coordinates. You'll learn more about this in Calc 3, but I just thought it might be fun for you to play with this and kind of understand something about this. Now, drawing the solids of revolution is not easy in Desmos 3D. It requires some work. I have done this. You might actually, so this is the definitions of that. I actually had to do 3 different pieces to get basically, if I look at it in this orientation, then this first one is the top piece. In fact, maybe I could just color them all different colors. Okay, so that top piece is gray, the bottom piece is orange, and then the outside piece is green. And these things might make more sense to you after we've covered our lesson on parametric curves. These are essentially parametric surfaces in 2 dimensions. But suffice it to say, this essentially asks you to understand a new kind of set of things about how graphing works, which is not entirely unreasonable, but maybe not where you want to be spending your time. Okay, so there are 2 other ones that are a little bit more accessible. One is CalcPlot 3D, and I actually want to start, I'm going to start from where this comes from. In fact, I'm going to look, so if I just do a search for CalcPlot 3D, then the one that comes up in LibreText is the one that you want. Okay, so this is the default view. They basically have a tendency to, anytime you add a new graphing thing, they give you a sample thing to graph in that type of medium. So I'm going to just X that out, and I'm going to add to graph. All the way down at the bottom, I want a surface of revolution. And they give you a sample automatically. So I want to say the top curve is going to be still y of x is square root of x, but the bottom one is going to be y of x equals 1 over x. Okay. And this is going from x equals 1 to 4. And the axis of revolution is the y-axis, which is x equals 0. All right. Now, this isn't really showing anything. I think I might need to hit graph in order to update that. Now, it's not showing anything until I actually ask it to rotate. So if I ask it to rotate the region, oh, I know why it's not doing this. It's because I don't have this selected. Okay, so there's my region. And if I rotate it around the y-axis, there it is. Now, there's some problems here. One is these axes aren't set up to be in the right place. So I'm going to come up here and I'm going to click on this button next to the graph. And I'm going to set my x values need to go up to 4, but let's make them go a little bit beyond that. So it needs to go up to 5. And because I'm rotating around the y-axis, it should go, the y values also should go to -5. Now the y minimum really can go from 0, but let's say -1 to 3, because I think the y values are really going from 1/4 to 2. So let's give ourselves a little bit of room there. And then the z, basically z and x are going to be the two that have the same, they should have the same scale. So that should go from -5 to 5. And I'm not really sure about these clips, but I want to set -5 to 5. Okay. And then I'm going to click on graph to rescale everything. I'm going to click on that to hide it now. And now I can rotate this around and I can see that solid of revolution. If I drag it around, this is one of my biggest complaints about this particular tool is it is very chaotic to move around. I don't really understand what the mouse movement is. And I think, honestly, because of the way that these three technologies behave very differently with this drag, it's made me realize that I'll bet that that's a pretty hard computing problem, figuring out what a drag should mean when I'm dragging something on a 2-dimensional plane and trying to interpret it as a 3-dimensional object manipulation. Anyway, this tool is pretty nice for a lot of reasons. I'm going to unrotate that region now and scroll down here. So there is an opportunity to show a representative rectangle. And so you can see that representative rectangle show up in that region. And I can choose where in my X interval that rectangle is showing up. And I can go and revolve that one representative rectangle. So this is giving me a representative cylindrical shell in that volume of revolution, or that solid of revolution. Okay, and then another thing that it can do is it will give me, basically divide that interval into n subintervals and give me washers or shells. And so I can decide how many of those there are, and when I revolve the whole solid around, it actually revolves it around as shells. So you can see the approximation with the Riemann sum and how that approximation gets better as the n gets bigger. Or I can see the representative, if I hide this, I can just see the representative solid. There's a couple other things that you can do in here. I think, trying to remember, I think I found a couple of settings that were helpful. So I think it's helpful to have the default 3D view with y-axis up, and I think that's how it showed up when we actually when we opened this. But another thing that I saw, I think it's in here. If I go on, click in this gear, then this gives me settings for my solid in particular. So I kind of like to have a little bit of transparency so I can see through that, so I can see all the parts. And sometimes I also like to hide the edges and just see it as a solid without the edges. So it's up to you. You might prefer to have the sort of wireframe or not. But this is a nice tool just to kind of see how those revolutions are working. And it's very simple to operate too. The last one is the Geogebra 3D. And so this is another platform for free computing and graphing. And they have a 3D calculator. So I went and I set up those two functions again. And the thing that I'm going to do to create the solid of revolution, they don't have a thing for creating a solid of revolution, but they do have surfaces of revolution. So what I'm going to do is I'm going to type in the word surface. And if I click on this, I'm going to use the one that has a curve, an angle, and a line. So the curve, I'm just going to say F. Angle is going to be 2 pi. That basically says how much rotation do you want. And the line is going to be the y-axis. So that has gone and rotated this entire curve. And again, the drag is difficult here. Let me actually change a couple things about that. So let's go into the gear here. I'm going to stop showing the XY plane. And I'm going to go into settings. And I like to not show the Z-axis. And in basic, I also don't like the colored axes. I want the axes to be black. And I want to set y-axis is vertical. Okay. Now, that gives me a little bit easier to manipulate setting. So she says. Okay. So the thing is, this is drawing too much of the surface. So I'm going to go back to this f of x, and I'm just going to put a comma and say x is going from 1 to 4. So 1 less than or equal to x less than or equal to 4. By the way, when I draw this less than or equal to, I just put the less than sign, and afterwards I hit the equals key, and that changes the symbol into less than or equal. Okay, and again, I'm going to do this in here with G2, where 1 less than or equal to x less than or equal to 4. Okay, so now I see that surface of that one portion of the curve. And I'm going to do it again, surface of G, where the angle is 2 pi, and I am also going to use the y-axis. And so this gives me the upper boundary and the lower boundary But then I need, I think, so I need the closing bit, and I am going to create a segment. And if I know where those 2 points of intersection are, I'm going to create a segment. And I'm going to do a segment with 2 points. So open up new parentheses for a point. So down here, that's going to be x is 4 and y is 1/4. So 4, 1/4. And notice we are in 3 dimensions, so I actually need to put a z-coordinate, and the z-coordinate in the xy plane is always 0. And close parentheses, and the other point would be for this upper curve, that's where y equals the square root of x, so the square root of 4 is 2, and the z-coordinate is 0. Okay, so there's that segment. If I hit enter, that segment is called H. So now I'm going to do another surface where I'm going to rotate H around by an angle of 2 pi and going around the y-axis. Okay, so now I can see that surface here. And I can go and change the colors of all of these and change the opacities of them. There's lots of settings that you can change here. I think if I put style, if I don't want the grid on it, I can just set the line thickness to 0. And then the color, maybe I want all of the colors of them to be this nice shade of blue. And then I'll do the other one to be the same nice shade of blue. And maybe I'll also take the lines off. It's up to you. You can play with it a little bit. Okay. The one other thing that you can do here that makes this look a little bit like the CalcPlot 3D, instead of setting that that angle at 2 pi, I can set my own angle. I'm going to call it alpha. And I'm just going to say, I'm going to create a slider off of that. And I am going to look at the settings of alpha. Now, that is going to go from 0 to 2 pi. And I have learned from some experience that it's nice to choose an increment for that. So I'm going to say 2 pi over 400. That basically says that that's the granularity of that slider. And so that is set at 0 now, and I'll go ahead and set it somewhere in the middle now. And whenever I have this 2 pi angle of rotation, I'm going to change that to an alpha. Turn that off. So that's going to be changed to alpha. Just going to copy this. Copy. Paste. And one more. Okay, and now when I drag my alpha, I can see that complete. And see, this is why I use the increment of 2 pi over 400, is because it doesn't quite get a full revolution. So let me go back to that. See, it didn't save that for some reason. This is a weird thing. Like the menus, the settings menus don't always work for me in GeoGebra. 2 pi divided by 400. All right, click out of there, and now I should be able to get that. No. See, it's only going up to 6.2. some weird mysteries into like how those menus work. It's a little glitchy. But there you go. There's a few things that you can play with.